This is 12.1 Goodness of Fit Test Part 1 video. We're going to go ahead and take a look at a situation where someone makes a claim about some distribution or about how some values are distributed with certain characteristics. And in this situation, imagine you have a bag of M&Ms, chocolate M&Ms, and we know that the company says that the colors are distributed in this way: 13%, 14, 20, 16, 24, 13% red. Is this true? Well, how would we know it's true? We would have to test it out. You get a bag of M&Ms, open them up, and then you count the colors. And then you look to see if the colors follow the same distribution, right? The percentages. And so here's an example. We open up a bag of M&Ms. There are the M&Ms. And here are the observed values. You get 6, 7, 12, 7, 6, and 3. Total of 41 M&Ms in the bag. Now, how would we check to see if these values should match up to these percentages? Well, we want to check to see 6 out of 41, 7 out of 41, right? Look at the percentages. And so be able to check to see if that works. The way we do that is, first, based off these percentages, we check to see if what we observe matches up to what we expect to see. So for example, if there's 41 M&Ms, 13% should be brown, or around 5 of them. 14% should be yellow, or around 6. 20% should be orange. We get it from here, and that's again around 8. So you can see we have these expected values. And so the hypothesis test we're running, a goodness of fit test it's called, is to check to see if the colors follow the distribution stated by the company, and then the alternative is that the colors do not follow the distribution. So they either do or don't. And so you have these observed and expected values. You want to see how close they are. That's actually called the residual, which we learned in chapter 4, I think, or in regression. You see how close the observed was to the predicted. So not that bad, actually. It looks like maybe. Well, we'll see, right? And then there's a calculation we do to get a test statistic. Now, we're just showing you the idea by hand right now, but you could use StatCrunch. The test statistic is the sum of the observed minus the expected, this one here, squared, get rid of the negative, and then divided by what we expected. And so this test statistic is called the chi-squared, C-H-I squared, or chi-squared test statistic. When you add up those values, you get a number. That number would then help us determine if the colors follow the distribution, if we observed what we expected to see based off of that distribution. And then you would be able to do that. And so if we have a small chi-squared number, if it's very close to 0, right, we would expect these values to be close together, right? Because if these are the observed and expected are close, then these numbers are small. And if our test statistic's very big, or what we observe is very different than what we expect to observe, your chi-squared value be very big. And so that's what we're doing here. That's the idea. And then what we're going to do is then look at this chi-squared, and then either you have to use a calculator, or like look at a distribution like we did with the test statistics for T's and Z's. This is just a new one called chi-squared because of our situation.